In this question, an external force of 300 newtons is applied to a crate at an angle of 35 degrees below the horizontal. So the crate has a mass of 50 kilograms and it moves horizontally across the surface at a constant velocity, which means acceleration is zero, because acceleration is the change in velocity over change in time. If an object is moving at a constant velocity, acceleration is just zero. So our objective is to calculate the coefficient of kinetic friction. I'm going to start off with a diagram. So I'm going to first specify the coordinates. Positive x, I'm going to choose right as positive x, up as positive y. And then let's look at the forces acting on the crate. So weight is acting directly downwards, and then we apply a force of 300 newtons at an angle of 35 degrees below the horizontal. So that is the applied force. And then the normal force, the surface is pushing the crate up, so normal force is acting up. And then pay attention to the relative magnitude of the forces, guys. Before that, let me explain you the next force, the kinetic friction force. The crate is moving, so it is not static friction but kinetic friction. Friction always opposes the motion. That's why the kinetic friction is acting to the left. The crate is moving to the right. And pay attention to the relative magnitude of forces. The kinetic friction acting to the left should equal to the magnitude of the component of the applied force which is acting to the right. Okay, so that is important to know. So we have to pay attention to the relative magnitude of the forces. And then again, weight is equal to mg. So mass is 50 kilograms, and then the next, the applied force is 300 newtons. It is given in the question. And again, we can look at this applied force. It is acting at an angle of 35 degrees below the horizontal. So now I'm going to draw a vector diagram to show this applied force and the two components acting along the x direction and y direction. The component acting along the x direction is equal to force applied times cosine of 35 degrees. And then the y component is f sine 35. This is, you have to use your knowledge on trigonometry to find out the x and y components of the applied force. Okay, now we have defined the coordinates and then applicable concepts. This is chapter 5, section 5.1, which involves friction. And let's see what we're trying to find, and let's see the expected sign of what we're trying to find here. So we're trying to calculate the coefficient of kinetic friction here, and the unit, there's no unit for the coefficient of kinetic friction, and then the sign. In general, the coefficient of kinetic friction should be positive. It's not a vector, it's just a coefficient, but it's not negative. And then let's plan our solution. So before we plan the solution, I'm going to create this table to identify each force acting on the crate and then x and y component of each force. Normal force acting directly upwards, there's no x component, y component is positive. Kinetic friction, friction always opposes the motion, so it is acting to the left. And then the y component of the kinetic friction is just a zero. And then the next force is the, I'm going to talk about weight. So weight is acting in y direction. There's no x component and it's acting directly downwards based on our coordinate system. It is negative mg. And then the applied force F, we have to find out the x and y component of the applied force. The x component is F cosine 35. You can see it from the vector triangle, and then the y component is F sine 35. It's acting downwards, so it's negative F sine 35. And now let's see the equation. So we can use the equation for the kinetic friction. So we know kinetic friction is equal to coefficient of kinetic friction times the normal force. And then we can use Newton's second law. And I'm going to use the component form of the Newton's second law because we have to solve for the variables in x direction and y direction separately. So let's use the component form of the Newton's second law. So net force in x direction is equal to mass times acceleration in x direction. We have to look at all the forces acting in x direction. And then net force in y direction is equal to mass times acceleration in y direction. So now we have the equations, and now we can execute our plan. Okay, so it's really easy to execute the plan once you have all the forces acting in x direction and y direction, and if you have figured out the equation. So I'm going to use the Newton's second law in x direction, and look at the table. All the forces acting along the x direction, it's right there. You have the negative Fk plus F times, that is the kinetic friction, plus x component of the applied force is equal to mass times acceleration. But now the crate is moving at a constant velocity, which means acceleration in x direction is 0. And kinetic friction is equal to F cosine 35. You just have to rearrange the equation. And now I'm going to use Newton's second law in y direction. Net force in y direction is equal to mass times acceleration in y direction. Acceleration in y direction is 0. Again, the crate is not moving in y direction, so there's no acceleration. And look at the y components. I have normal force minus mg minus F sine 35 is equal to 0 because acceleration is 0. And then if you solve for the normal force, you get normal force is equal to mg plus F sine 35. I'm going to solve for normal force. I think you guys know what I'm going to do next. I'm going to use this normal force to get an equation for the kinetic friction on the crate. So normal force is mg, m mass 50 kilograms times 9.8 plus 300 newtons times sine 35. And if you add these two, you will end up of getting 662 newtons. And we know that normal force times the coefficient of kinetic friction is equal to kinetic friction acting on the crate. And the coefficient of kinetic friction is an unknown, so that's what we are trying to calculate here. And I'm going to use this equation for the kinetic friction. I'm just going to substitute for Fk is equal to mu k times normal force is equal to F cosine 35. And then I'm trying to solve for a mu k, so I'm going to separate it on one side of my equation. F cosine 35 divided by the normal force, and then I'm just going to substitute for the force applied, which is equal to 300 newtons times cosine 35 divided by normal force. (662 newtons, we calculated it. If you solve for mu k, guys, you will end up of getting 0.371. So that's mu k. So let's check and evaluate. Is the solution complete? Yes, it is complete. We solve for mu case. Sign of the answer correct. There's actually no unit, and then magnitude of the answer is reasonable, less than 1. So understand the process, guys. So let's go back to what we did. So before that, I'm just going to highlight our answer. And we started by visualizing the problem. It is really important to visualize the problem. Why? Because it actually helps us to identify all the forces acting on the crate. So you can see normal force is acting up, and then there's weight acting on the crate, and then the applied force, and then kinetic friction. And we resolve for the x and y components of the applied force, and we specified the coordinates. Really important. You can see in the exam you get points for specifying your coordinates. Very important. Make sure you guys do that when you solve a problem. And then we created this table. It is a lifesaver. It's going to save our time a lot if you come up with a table like this. It's very clear. You have a clear direction, and then we use Newton's second law, the component form of the Newton's second law in x direction and y direction. We came up with an equation for the normal force, and we calculated the normal force, and we used that to come up with an expression